Good morning, class. Today is today is October the 21st. So this is the video for October the 22nd. And so today we're going to continue on dopant diffusion. And today I'm going to introduce to you that it's usually a two-step process. And we've covered the first step. The first step is dopant gas on. And sometimes, okay, in the textbook this is called infinite source, or in the notes it's called constant source. Okay, but the idea is the gas is on, and that results in this profile over time. NS, and basically it's that complementary error function NS times 1 minus the error function of x over L, where L is defined to be 2 to the square root of dt, and it's sort of not so much a definition as an actual thing, it's the diffusion length. Okay, so that's pretty easy, really. It's an easy result. The error function is, not friendly. I mean, in the sense that, you don't know what it is until you look it up in the table. And actually, let me try and draw it a little bit better. So this is on a linear scale. In the homework, you're asked to so it looks something like that, where on a linear scale it goes down linearly, and then it does that sort of thing. Okay, so that's what you get in the infinite source diffusion, and as a function of x. Okay, and time is contained in the diffusion length L. So basically, as time goes up, L goes up, and this thing moves over because x over L is the parameter here. So I'm not going to, okay, I could draw curves at different times. Okay, this is a linear scale, by the way. I'm not going to draw it at different times because it's sort of like you do this step. It's like the homework. You do this step and you put in some dopant. And the idea is that you put in some dopant near the surface. And you then want to characterize that you've put in what's called a dose, which is Q. And that's equal to the integral of n of x dx from 0 to infinity. So it's basically that area. And now, of course, you have to put in, this is n of x. You have to put in that error function, okay? And so it becomes this, this integral you have to look up, the integral of an error function. But the result is pretty simple. Q is equal to NSL over the square root of pi. Now, NS is the dopant atoms per unit volume, and so you multiply times the diffusion length, and so that gives you the dopant atoms per unit area. So the idea is here that you're going to do dopant diffusion in 2 steps. And in the first step, you're going to have the gas on, we call that infinite source or constant source. Basically, there's a source, the gas, above the wafer. And you're going to do that for a certain amount of time, and you're going to get this distribution. And then basically, you're going to do it. The idea is to do it until you get a certain Q, a certain dose of dopant atoms per unit area on the surface. And the idea is that that's kind of on the surface of the wafer. All right, and you know, then the next step, step 2, is to turn off the gas. And diffuse what is there for some time. So now let me just go through the solution and explain to you what we're getting at here. But basically, this is sometimes called constant dose. But the idea is that that you've turned off the gas, and now you're going to diffuse what's there on the surface. Check my focus. All right, and now basically, you're still solving the diffusion equation. Okay, so now, with Q, with a dose Q, all right, solve partial of n with respect to t is equal to d partial squared of n with respect to z x squared, with the boundary conditions that you have a certain dose Q. And I'm just going to show the result, and then we'll talk about it a little bit. So basically, the solution is a Gaussian. So this is again a linear scale. And the solution then is n is equal to let me write it this way, 2 over root pi times Q over L e to the negative x squared over L squared. And the idea is that the boundary condition, the main boundary condition is the integral of n of x dx for any time okay, is Q. So let's think about that for a minute. What I'm telling you is that those pesky mathematicians figured out that a Gaussian is a solution to the diffusion equation. Okay, you plug it in, and I'm not going to do it, but if you plug it in, remember L is this. Let me box that so we never forget that. If you plug it in, it works. And furthermore, the integral is Q. And if you look at it, L is proportional to time. So as time goes on, so this is T, and then let's say this is T1, and then if I go to T2, bigger than T1, all right, that goes down, because Q is a constant, all right, and so um, uh, L goes up with T, and so Q over L goes down with T. That's the, that's at the surface. This is X. And then also it gets broader because also L here in the Gaussian goes up with T. And it makes perfect sense what goes on. Okay, so let me, do it like this. And let me do a further one over here. All right. And so let me try and shade that area. And the point is that that's Q also, meaning Q is the area under the curve. Let me write it differently because I don't want you to get confused with calling it an area or anything like that. It's the integration. And it's a constant. And that's it. Okay, that's it. We're done. Okay, because basically you put in the dose with the first step with the gas on, and then you turn off the gas. Now, I want to make clear something. All right, that there's a little bit of a disconnect. Okay, so T equals 0 here starts after step 1. All right. So you have to treat them as two distinct steps. Okay. You put in the dose with step 1, and there's a time involved, and there's an L involved there. Okay. And the confusing thing to students here is that, okay, once you're done with that step, there's a new L here. All right, you do that step, you get a certain Q, and then that's it for step 1. All right. Then over here, time starts over again, L starts over again, and there is a little bit of a disconnect because, of course, then L starts at 0, right? Because time starts at 0. And so what I'm telling you is that you can't start this one. You can't start this one at T equals 0. T equals 0 here is kind of meaningless because basically at T equals 0, L would be equal to 0, and this thing would be up there above the ceiling and have, be like a delta function there. And so while T equals 0 starts over again for this step, you have to like plug in a time, and that's the point of the homework, is to show you that you have to plug in a time sort of a little bit longer, and basically the idea is that over here this is kind of L from step 1, and then you have to start with an L for step 2. Let me write it the other way. Okay, let me just write L. So you do this step, you get a certain Q. There's an L1 associated with that, and basically you kind of like just forget about that. Okay, you're like, okay, I'm done with that. I got my Q. All I really care about from this step is what is Q? What is the dose that I put in? What are the dopant atoms per unit area I put in? Then step 2, time starts over again, and so L is a new time. All right, you run this for a certain amount of time. So for example, you might have run this for 4 hours or something like that to get a certain Q. And then this one here, okay, time starts over again. You turn on the oven with no gas, and you run it for a while. And after you run it for a while, you get a certain distribution. And what I'm saying is that for the new time on this step, there's a certain times from 0 that don't make any sense. All right, for example, think of it this way. Okay, I got this distribution of the error function. All right, and now I'm going to start the timer over again. And let's say I ran this step for like a second, you know, or something like that. All right. Now, in reality, if I ran it for a second and I plugged in L would be some tiny, tiny number. It would be up. Okay, that doesn't really happen. Okay. If I run this step for a second, I still have this distribution reality. Okay, I haven't changed it. Checking my focus. All right, it's okay. Let me see. Okay, you can read everything. I apologize for that. All right, so step 1, you get a Q. Step 2, time starts over again. You run the furnace for a certain amount of time with no dopant gas. And what I'm saying is that you have to run it for some time, okay, such that the L over here is bigger than this L over here, or else the solution won't really make any sense. Now, once you do that, okay, for a certain time, okay, you get a Gaussian distribution, and then as you continue to run time, the integration under this curve remains constant, and so what happens makes perfect sense. Okay, the surface concentration goes down, and it spreads out more. And so basically the idea is that, okay, let's say I wanted to achieve, you know, and I'm running, you know, I'm getting kind of, but let's say I wanted to achieve that level of dopant at that distance. That would tell me how long I have to do it to get over there. And that's it basically. So step 1, put it in the dose Q. Step 2, take that dose, time starts over, okay, remember that, and then you run it for a certain amount of time such that that surface distribution broadens out and reaches a level at where you want your junction depth to be. And I'm not going to get into details about, you know, junction depths and wafers and stuff like that. I'm just going to tell you right now, all you need to know in this course is, all right, if I give you the problem saying I want a certain N at a certain depth, you know how to do it from this equation. All right, and that's it for today. We're only covering diffusion this week. So the next lecture is a review, and then a week from tomorrow is the quiz.